So this is my oral presentation on nanoparticle-based vaccines, the key to stopping malaria by me, in other words, my research paper. So there's the abstract. Vaccine development and implementation is one of the most important advances in modern medicine in the last century, resulting in millions of lives and increasing the productivity of human society. Nanoparticles are small polymer particles with a wide range of potential applications, including vaccine development and delivery. Using this technology has been shown to result in a stronger immune response and better efficacy of the vaccine. Malaria is an important and common worldwide infectious disease afflicting millions of people across the globe. It is caused by the Plasmodium parasite, which exhibits a complex life cycle with multiple stages, which may allow development of vaccines to interrupt the disease process, utilizing nanoparticle technology to develop a malaria vaccine that has been evaluated in numerous animal models. Clinical trials have been conducted in humans to assess the efficacy and safety of these agents. Additional research is needed, though, to fully understand the impact of these interventions on disease prevention. There is ongoing need for more efficacious and safe vaccine candidates to prevent the possibly eradicate malaria in the future. That's basically the rundown. Let's get into it. Vaccines are utilized to deliver an antigenic substance into a person's body. To activate their immune system and generate adaptive immunity against a pathogen, vaccines have been used to eradicate or control multiple important illnesses: smallpox, rinderpest, polio, tetanus, mumps, yellow fever, measles, etc. However, despite these significant triumphs, the search for innovative and advanced forms of vaccination persists to combat the continuing diseases that continue to plague the biosphere. Nanoparticles are spherical, polymeric particles composed of natural and artificial polymers. They range in size between 10 and 500 nanometers. As a benefit of their spherical shape and high surface area to volume ratio, these particles have a wide range of potential applications. One such application is their usage in delivery of vaccines. As you can see, this is nanopolymers right here. I haven't gotten to this part yet, but basically what I'm going to do is I'm going to explain different types of nanopolymers, how those are used in vaccines, what vaccines they're used in, how different ones have different effects, really get into it so we can provide a full understanding of how these nanoparticles engage in the vaccine process. Next paragraph. The application of nanotechnology to vaccine development promises many advantages, such as better lymph node accumulation, antigen assembly, and presentation, and unique pathogen biomimicry properties. The usage of nanoparticles to display or transport antigens shows a potential alternative to traditional vaccines. Also, the adaptability of nanoparticle platforms allows for quick vaccine development in response to emerging infectious threats, contributing to the agility needed to combat evolving pathogens. The recent success of nanoparticles-based Moderna, Pfizer/BioNTech COVID-19 vaccines shows a promising future using nanotechnology in vaccine development. Nanoparticle-based vaccines as a whole represent a promising and indispensable strategy for fostering international public health, providing a scalable and adaptable and effective solution to combat diseases. Again, I'm going to have a table right here. It's not there yet. It's going to be there. Again, resulting from the nanopolymers. It's going to be a table showing the type of nanopolymer, what vaccine it's used in, the dimensions of that nanopolymer, and the disease it's assisting in the name of the vaccine that it helps in. One infectious disease that currently afflicts a large part of humanity globally is malaria. Malaria is a life-threatening disease spread to humans by Anopheles mosquitoes. It is mostly found in tropical Africa, South America, and Southeast Asian countries. Sorry about that. Anopheles mosquitoes. The infection is caused by Plasmodium parasite. According to the World Malaria Report, more than 100,000 people died from the disease in 2022. These staggering numbers have urged for the advancement of an effective malaria vaccine. The country where malaria is the biggest health concern is Nigeria. Nigeria is an African country on the west coast, and in 2021, the country had 68 million cases of malaria. The country where malaria is the biggest health concern is Nigeria. Nigeria is an African country on the west coast, and in 2021, the country had 68 million cases of malaria. Nigeria alone accounts for 27% of the global malaria burden. This burden not only affects the people, but also the economy. Malaria-related absenteeism and productivity cause Nigeria to have an annual loss of an estimated $1.1 billion. Malaria is a mosquito-borne infectious disease caused by the Plasmodium parasite, which inflicts a variety of detrimental effects on the human body. The initial symptoms often include fever, chills, flu-like conditions. These can lead to severe complications that affect vital organs such as liver, spleen, brain. One of the common manifestations of severe malaria is cerebral palsy, which may result in seizures, impaired consciousness, and in some cases, coma or death. The pathophysiology involves the parasite's ability to disrupt the normal functioning of red blood cells and cause systemic inflammation. Furthermore, the cyclic nature of malaria exacerbates the toll on the body, with recurring fever, anemia contributing to the overall debilitation of the infected individual. Additionally, the sequestration, which is when red blood cells break down and clog in these small blood vessels, further exacerbates the disease impact on vital organs such as brain, kidneys, and lungs. Understanding these intricate interactions is pivotal in advising effective strategies for combating this infectious disease that continues to plague the world. Combating. Malaria poses a formidable challenge to the human immune system because of the complex nature of the Plasmodium parasite and its ability to evade host defenses. The parasite has developed sophisticated mechanisms to survive within the human body, including alternating the surface proteins of the infected red blood cells, making them less recognizable to immune systems. Additionally, the parasite goes through various life stages, each presenting different antigens and avoiding immune recognition. The Plasmodium species exhibited genetic diversity, enabling them to adapt to evade immune responses. This complicates the development of a broadly effective vaccine. Furthermore, the mosquito's vector role in transmitting the parasite adds an extra layer of complexity to malaria control efforts. The continuous evolution of the parasite and its ability to exploit various strategies to avoid immune detection make developing resistance challenging, highlighting the need for compressive and innovative approaches in the fight against malaria. A successful malaria vaccine could result in several hundred of thousands of lives saved and billions of dollars in savings from lost productivity. Many countries in the world could benefit greatly from stable and efficient protection against malaria. The burden on the people would no longer wear down the health, and economic systems of societies. Vaccine requirements. For a vaccine to be successful, it has to be a good safety profile with low risk of serious adverse effects. It should result in a robust immune response in the population receiving it and be effective at reducing risk of malaria. It should be easy to produce and store to allow for large-scale production and distribution widely. Finally, it should be inexpensive to produce so that it can be widely utilized in different parts of the world where resources allowed for disease prevention may be constrained. Recent studies have shown the use of nanoparticle vaccines can open the gateway to preventing malaria. One recent nanoparticle acted as a malaria transmission vaccine, or a TBV. The study strongly supports the usage of these nanoparticle-based vaccines, particularly the PFS230D1E2P. Let's just call that PFS for now. A nanoparticle and interlayer cross-linked multilayer vesicles, ICMVs, as promising approaches for malaria control. TBVs are crucial in breaking the cycle of infection between human hosts and mosquito vectors. The study of PFS nanoparticles demonstrates the successful fusion of PFS to a 60-copy multimer of catalytic domain of dihydrolipol acetyltransferase protein E2P, resulting in stable homogeneous single-component nanoparticle with high production yields. This nanoparticle, when used in two vaccinations of New Zealand white rabbits, elicited a potent durable antibody response with high transmission-reducing activity, TRA. Moreover, the PFS nanoparticle, formulated with its suitable adjuvants, for translation to human use, presents a potent human transmission-blocking epitope with PFS. These studies suggest that this single-component nanoparticle vaccine has the potential to simplify production pipelines and reduce the cost of manufacturing while providing an effective tool in the fight against malaria. Additionally, the ICMVs, discussed earlier, shown enhanced immunogenicity and potential for dose sparing of adjuvants, further highlighting the promise of nanoparticle-based vaccines in malaria control efforts. In another study, researchers investigated the immune response triggered by nanoparticles containing multi-molar stapled lipid vesicles carrying a recombinant plasmodium vivax circumporozoite antigen VMP001, along with monosphorophyll lipid MPLA, an immunostimulatory agonist. These nanoparticle vaccines demonstrated the potential to induce tighter, high avidity antibody responses against MMVM P00, lasting over a year in mice at significantly lower doses compared to traditional adjuvants. Moreover, comparable to soluble VM P001 mixed with MPLA. The nanoparticle formulation elicited broader humoral responses targeting multiple epitopes of protein and produced a more balanced Th1/Th2 cytokine profile from antigen-specific T cells. The study also dove into an understanding the underlying mechanisms revealing nanoparticle vaccination promoted more robust germinal center formation and expansion of antigen-specific follicular helper T cells, suggesting that nanoparticle vaccines have the potential to enhance the durability, breadth, and potency of humoral immunity by modulating key elements of the B cell response. Clinical trials of anti-malaria vaccines. The nanoparticle-based malaria vaccines development has progressed rapidly over the last few years. The first vaccine was widely studied is the RTS vaccine, which used to circumporozoite protein. This antigen causes an immune response to the pre-erythrocyte phase of malaria parasite. This protein was combined with AS01, which is an adjuvant for this vaccine, AS01. The use of adjuvants increases the immune response to the vaccine. Sorry about that. Here we go. This RTS AS01 vaccine was studied in phase 3 randomized clinical trials. This trial was conducted in 7 sub-Saharan countries, and 15,460 children were enrolled in this trial from 2009 to 2011. 3 doses of the vaccine were injected intramuscularly, 1 month apart in the active group. The control group received non-malaria-related vaccine. The vaccine resulted in an efficacy of 50% in reducing the risk of the first episode of clinical malaria. The risks of severe malaria reduced by 45% in the group receiving the vaccine. The main limitation of this vaccine was the low efficacy of the vaccine. Moreover, the efficacy of the vaccine declined significantly with time. Additional vaccines are being studied in search of better efficacy and more durable protection with the vaccine strategy. More recently, another vaccine candidate had been studied in phase 2 clinical trial. In this trial, a low-dose circumporozoite protein-based R21 alongside 2 different doses of adjuvant matrix and were tested in children ages 5 to 17 months in Burkina Faso, Africa, in 2021. The vaccine series consisted of 3 doses, each 4 weeks apart. 450 children were randomized in 3 groups, and 2 groups receiving the anti-malarial vaccine, and the third group receiving a control vaccine. Participants vaccinated with the R21/MM vaccine demonstrated high levels of malaria-specific protective antibodies 28 days after 3 doses of the vaccine. The vaccine showed an efficacy of 77% at preventing malaria at 6 months as compared to the control arm. These vaccines also showed a favorable safety profile and were well tolerated. The beneficial effect of this vaccine was confirmed in a follow-up study in which these children returned to receive a booster shot 12 months after the initial vaccine series. The high-dose vaccine group maintained an efficacy of 80% in preventing the first case of malaria. The promised result of this phase 2 trial support further evaluation of the vaccine in a larger phase 3 trial in different malaria transmission settings. An important advantage of this new vaccine is the potential for low-cost, large-scale manufacturing. These factors can help in developing and deploying this for similar vaccines, widely support efforts to control, systemically eliminate, and hopefully finally eradicate malaria. As for my discussion element, there is work that needs to be done. I essentially basically just reiterated what my related literature was instead of going into how these experiments and how these studies more prove my thesis. So basically what is here is not going to be what's going to be in the final copy. It's going to all be rewritten, and I'm going to set up meetings to get that checked over and looked over once it is rewritten. But as of right now, this is the not final copy, this is the draft of my paper that I'm presenting. I have done the citations. There are a couple that still need to be done. I have been using the citation generator as told. And so far, I think I'm making really good progress. There are definitely big changes that need to still be implemented, but I do feel confident in with changes that I am implementing and with what I will have to present the next time, or rather when a final copy is going to be shown. Thank you.